Greetings, logic students. I hope you're having a good day today and making it through another day in the plague years. Maybe this will distract you from what's going on. Because we're now ready to learn what is known as truth functional logic. It is also sometimes called symbolic logic, mathematical logic, or propositional logic. An ancient version of this type of logic was first discovered in ancient Greece and Athens in the early 3rd century BCE by a group of philosophers known as the Stoics. This way of doing logic, however, was forgotten because of the great success of Aristotelian logic, which had been started before the Stoic version, and which also meant that something rather important for our modern times, called the truth function, was forgotten until the late 19th century, when propositional logic was revived first by George Boole, and then further developed by the great logician Gottlob Frege, and then further developed by Bertrand Russell, Alfred Whitehead, Ludwig Wittgenstein, Charles Peirce, and others in the 19th and 20th century. Now, in order to begin to get into this, we have to start at the beginning. And it's like putting little Lego blocks together. I'm going to give you little basic units of thought that'll build into larger and larger ones. And it's important to master each level as we go through it in order to deal with the more complex level as we build things up. So that's just a little word of advice. So let's get started. Now, symbolic logic is sometimes called propositional logic because in it we combine simple propositions into compound propositions and then use the ways they are combined to determine the truth value of the resulting compound. Now, a simple proposition is one that cannot be broken down into other propositions without losing its meaning, while a compound proposition can be broken down into meaningful components. Consider the statement, Han Solo was a smuggler and a starship pilot. Well, it has two propositions that are combined with that and the two propositions are Han Solo was a smuggler, and the other one is Han Solo was a starship pilot. So it's a compound proposition. But consider this simple proposition. The handsome smuggler kissed the enchanting princess. There's just one claim there, and so it's a simple proposition. And here's a few more examples for you. Han and Leia went to Cloud City means Han went to Cloud City. Oh, look at that. I gotta fix that. Han went to Cloud City and Leia went to Cloud City. Now, what you want to notice here is, remember previously we talked about how a proposition is the meaning contained within it. So it's not identical with the spoken sentence. So logically, Han and Leia went to Cloud City is a sort of shorthand for Han went to Cloud City and Leia went to Cloud City. Or suppose we say Chewbacca likes to eat and win at games, right, as C-3PO found out. Well, that has two components. Chewie likes to eat and Chewie likes to win at games. And then if we think of a negated proposition where we say something is not, it's considered compound as well, but in a special sense. Because if we look at a sentence like, Darth Vader is not here to help us, right, and we know he's not. It has the component, Darth Vader is here to help us, and it's negated, so it has a complex meaning. Now let's think about the form of propositions and arguments. Okay? First, consider two compound propositions expressed in English sentences. He is a hobbit and he is famished. And he is a wizard and he is angry. Now we can use capital letters, which we call constants, to stand for the component propositions in these compounds, and then create a dictionary for our symbolization. Right? So for he is a hobbit and he is famished, we can let H stand for he is a hobbit, F stand for he is famished, and that gives us H and F. Similarly, he is a wizard and he is angry. W will stand for he is a wizard, A will stand for he is angry, and that gives you W and A. Now, it's important to realize that the constants, the capital letters, are just shorthand for expressing the propositions. So H is just shorthand for he is a hobbit, and so forth. Now, also recall the notion of variables and constants, which might be familiar to you from high school algebra. Variables are lowercase letters beginning with P in our system. So our variables, and they're like the X, Y, and Z in algebra, but in logic we use P, Q, R, S, T, U, V, W, X, Y, and Z. And the constants are all the uppercase letters of the alphabet beginning with A. Okay? And constants then stand for the actual proposition, the particular propositions and the particular arguments, while a variable is a letter for which we may substitute a constant. So just like if you had x plus y equals z, and you could put any number you want in the x and the y and the z, so p, q, r, and s, t, and so on can stand for any proposition. A propositional form is in a formula consisting only of variables, so that when constants are consistently substituted for variables, the result is an instance of the propositional form as follows. Again, we let H stand for he is a hobbit, and F for he is famished. Then H and F is a substitution instance of the form P and Q. P and Q is the propositional form, and H and F is the instance. Similarly, he's a wizard and he is angry, W and A. P and Q is its propositional form, and W and A is an instance of that. So a substitution instance of an argument form is the argument that results from uniformly replacing the variables in the form with constants. Okay? And it's important to keep in mind, again, that P and Q are variables. It just means something like blank and blank. And as long as we always put the same thing in each respective blank, or it may help you again to think of it like the x's and the y's in algebra. So we can now look at 5 propositions and consider their form. 5 forms that will be essential in getting at the meaning or semantics of our language of symbolic logic. But first, let's think a little more about argument form. Consider 2 arguments, right? If he's a Jedi, then he is force sensitive. He is a Jedi, therefore he is force sensitive. Remember, when we put our arguments into standard form, we list the premises, number them, then we put a slash, which means therefore. So these are the premises and this is the conclusion. And over here we have, if he's a smuggler, then he knows a few tricks. He's a smuggler, he knows a few tricks. We give our dictionary, J for he is a Jedi, F for he is force sensitive. And over here, S for he is a smuggler, and T for he knows a few tricks. And then we symbolize it. If J, then T, J, therefore F. If S, then T, S, therefore T. And we can put those into their universal form by putting them, by using variables. And that gives us the universal form of if P, then Q, P, therefore Q. If P, then Q, P, therefore Q. And here we see these 2 arguments have an identical form. That means these 2 arguments are instances of the form if P, then Q, P, therefore Q. So both of these arguments have the same form or pattern of reasoning, and each argument is a separate substitution instance of the argument form. A substitution instance of an argument form, again, is the argument that results from uniformly replacing the variables in the form with propositions or proposition forms. Remember that when we use constants, again, we're only creating a shorthand for expressing the propositions. So really what this means is, if he's a Jedi, then he is force sensitive, but I'll just put the J and the F there to make it simpler to manipulate. To re-emphasize, here we have the form, and here we have the instance. Right? And I keep repeating this because it's so important. An argument form is then a formula consisting only of variables, so that when constants are consistently substituted for variables, the result is an instance of the argument form. Now, any artificial language has a semantics and a syntax. The syntax is essentially the grammar, or how you put things together according to certain rules, and the semantics is the meaning of the language. And the meaning of our language is found in our main connectives, which we can also call the main operators, because they operate on our formulas in various ways. And we have 4 binary operators and 1 unary operator. Binary meaning it involves 2 things, and unary, it involves 1 thing. So our first operator is the conjunction and it's symbolized by the ampersand. Our second operator is the disjunction, or, and it's symbolized by the V. We then have our conditional, the if-then, symbolized by the arrow. We have a biconditional, if and only if, symbolized by the double arrow. And we have the negation, not, symbolized by a tilde. So we're now going to define what these operators, our connectives, mean, right? We're going to get at the semantics, or the meaning, in our language. So consider our first proposition. Leia is on Hoth, and she needs to escape. Well, logically, that contains 2 components. Leia is on Hoth, and Leia needs to escape. And so we can symbolize that by L and N, using the ampersand to stand for the and. We're now beginning to get into turning our language entirely into symbols. Now, these 2 propositions are related by the and the resulting compound proposition is called a conjunction. The 2 component propositions are then called conjuncts, right? We could talk about the left conjunct and the right conjunct. And when we do this, we always give a dictionary or symbolization key, right, using capital letters to stand for the simple compound propositions. So that gives us L and N. But we want to think about the logical meaning of and wherever it occurs. So we're going to put it into universal form, right? And there it is, P and Q. So we could plug in anything we want into the P and Q, and that means whenever we find an instance of the form P and Q, we're going to know what it means. And here's what it means in English, and here's what it means in symbols. Right? A conjunction is true if both of its conjuncts are true. Otherwise, it's false. And this is how we define its logical meaning. So this compound proposition will be true as a whole only if it's true both that Leia is on Hoth and it's true that Leia needs to escape. And if we use our variables to stand for any possible substitution instances, we can define the meaning of and in what we call a truth table, which graphically displays all possible combinations of truth values in such a compound proposition. Now, truth tables are kind of interesting. They were formulated to express these meanings by the great philosopher Ludwig Wittgenstein, who lived in the 20th century. And it's curious, when he wrote it, he was a medic in the German army during World War I, in the trenches, under artillery fire, writing this beautiful little book called the Tractatus, right? The Philosophical Logicus Tractatus. And in the Tractatus, he comes up with this idea of truth tables to express the semantics or meaning of symbolic logic. And you'll read about that in logic comics. Look at the way we read this. True and true are true. True and false are false. False and true are false. False and false are false. And by the way, you have to memorize this, or you can't get any further in our course and will crash and burn. So, a word to the wise. So this truth table gives us the logical meaning of any conjunction in our language. In normal language, we might mean more than this, but as logicians, we're only interested in the logical meaning we abstract from the language. So, other English words are reduced to the core logical meaning of and that'll hold true of the other operators as well. So though all these sentences are very different in English, right, they all mean the same thing, or would be translated the same in our symbolic language. Leia is on Hoth, but she needs to escape. While Leia is on Hoth, she needs to escape. Leia is on Hoth, however, she needs to escape. And although Leia is on Hoth, she needs to escape. L&N. Now, one particularly fascinating thing about what we're learning here is that we're also learning the basis of how our computers work and our phones and any digital device. Every digital device you use and the computer you're using right now depends on what we're studying, right? In essence, a computer is made up of countless physical instantiations of the logical operators and or not. Let me explain what I mean. Consider a simple electrical circuit. Here's our power source, here's our battery, and we have two gates, right? And both of these little gates are open, right? And you have to close both gates to make the light bulb light up. Well, consider this one. That's like false and false, right? They're both open. Nothing happens, right? Or consider one gate is open and one is closed. That's like false and true, or true and false. One gate open and one gate closed. But if both gates are closed, true and true, then it lights up. This is the logical meaning of and instantiated into a physical object. There's something very curious and interesting about being human, is that we externalize our knowledge, and we externalize it in different ways. We have these ideas in our mind, and then we sort of build things that express them. And first we built this, right? And we can write it down and look at it and talk about it in English language. But then there's one genius of a fellow named Claude Shannon, and if you don't know about him, you ought to look him up, who had the brilliant idea that you could take this logical meaning here and put it into a circuit, right? And this is called a logic gate, and it's an AND gate. And every computer has millions of little AND gates in it, and it doesn't look exactly like this because we've learned how to engrave it and put it on tiny little chips and so on. But the idea behind an AND gate is basically this, and this is the logical meaning of AND. Now consider another statement. Luke is with Han, or Luke is with Leia, right? That's a compound proposition. And these two propositions are joined by the or, and the resulting compound proposition is called a disjunction. The two component propositions are called disjuncts, and we can call this the left disjunct and this the right disjunct. We make our little dictionary, H for Luke is with Han, L for Luke is with Leia, and we symbolize it with the V, using this V for an or, which gives us either H or L. And the logical meaning of this in our language is that a disjunction is false if both of its disjuncts is false, and otherwise it is true. And here we have our truth table, which gives us the logical meaning of it. True or true is true, true or false is true, false or true is true, and false or false is false. And this gives us the logical meaning or form of any disjunction. In normal language, or might mean more than that. But as logicians, we're only interested in the logical meaning that we abstract from the language. So other English words are reduced to the core logical meaning of or. Now, this is also part of the logical structure of a computer, and it's the other main logic, one of the other main logic gates that you find that make up every digital device. Let's think about that for a minute. Consider a diagram like this, where you have the two gates constructed like this. If they're both open, it doesn't light up. False or false is false. Now suppose just one gate is closed and one is open, right? True and false. Well, it lights up. True and false is true. Suppose the other gate is open and the other gate is closed, right? False or true is true. And of course, if both gates are closed, true or true is true. And this is, in essence, what we mean by or. And it's so fascinating to think that over 2,000 years ago, folks thought of the or, those great Stoic philosophers. And they thought about this and how you can think about how we put things together. And down through time, we finally come to Claude Shannon in the 20th century, who figures out this. And because of that, well, this class right now is possible. It's possible for me to be on a computer and be recording this video, and for you to be listening to the video on your computer, and for me to contact you on our phones. It's all because of this. How fascinating is that? Now, it's important to notice that the assertion of a disjunction is only making the minimal claim that at least one of the propositions joined by the disjunction is true. This is called an inclusive or, because it includes the possibility that both of the disjuncts are true. If I say you can have salt or pepper on those eggs, I do not mean to exclude the possibility that you might have one or the other, or you can have both. Often, though, we mean something different by using an or, not an are. But here, let me fix that. Got to go up on the board to correct it. As when we say the baby will be a boy or a girl. In this case, just speaking biologically. In this, and not as it were in terms of gender. Because we want to be very clear in what we say in logic, right? As when we say the baby will be a boy or a girl. In this case, we use the so-called exclusive sense of or, which means one or the other, but not both. We will learn later a special way to translate the sense of or, but for now, unless indicated otherwise, or is always meant in the inclusive sense. So we have Luke is with Han or Luke is with Leia, either Luke is with Han or Luke is with Leia, or even Luke is with Han unless Luke is with Leia. These are all translated as R or W. Our next operator is the not, and it's the other one you'll find in your computer or digital device. And let's consider an example of that by considering the great Jack Porkins. And indeed, let's take a moment to remember the great Jack Porkins, hero of the Battle of the First Death Star, okay, who died fighting against the Empire. Let's remember Jack, and we honor him here by using him as an example. Right? So, here we have the sad truth that the great Jack Porkins is not coming back from the battle. Now, when we symbolize this, we symbolize first the positive statement. J for Jack Porkins is coming back from the battle, and we all wish he had. Right? And then we negate it to get not J. And the logical meaning of a negation is very simple. A negation has the opposite truth value of the proposition it negates, and its truth table is very simple. If something is true, it is false. And if it's false, then it becomes true. So we could say, it's not true Jack is coming back from the battle, or Jack isn't coming back from the battle. That would all be not J, right? And they would all have the same logical form or meaning. And here's how you do it with wires and batteries, right? The other logic gate that's in your computer, right? And here what we have is an electromagnet. When the current runs through the electromagnet, it makes it into a magnet, right? So right now, there's no power going to the electrical magnet. So when this gate is false, right, when this is false, it turns into true, right? False is true. Now, if you make this gate true, it turns the magnet on, pulls the gate down, and the light goes off, right? And so true, then false, false, then true. Cool, right? And again, it's fascinating to think. I like to think of it actually as there's billions of tiny little creatures. Maybe they're gnomes, but microscopic gnomes, and they're just tiny gnomes. And they're all in our computers, flipping little switches like this, right? There'll be like a little gnome here who pulls it, and so on, turns the power on. All they got to do is sit in a chair there, turn the power on or off. Busy little gnomes. Or maybe they draw truth tables and send messages to each other. All right, now it's false, now it's true. Anyway, I like to think of that our computer is inhabited by millions, and if it's a supercomputer, even billions of tiny beings operating truth functions. Now consider this statement. If Yoda escapes, then he will go to Dagobah. And of course, all of us are familiar with the history of the Jedi and the great struggle against the Empire. So I know you know that Yoda did escape and go to Dagobah, right? We hopefully all learn this in our history classes in our schools. And we want to symbolize this. Y for Yoda escapes, D for Yoda goes to Dagobah, and that gives us if Y, then D. Y arrow D. Right? And the two propositions are related by the if-then, and the resulting compound proposition is called a conditional. The first proposition is called the antecedent, and the second proposition is called the consequent. And here's our symbolization. And here's the logical meaning of a conditional. A conditional is false if its antecedent is true, and its consequent is false, otherwise it is true. So true then true is true, true then false is false, false then true is true, and false then false are true. Remember, words in English or German or Sanskrit can have many different senses, different shades of meaning. This is true for if-then in natural languages, which can be taken to express things as different as cause and effect relations. Like we said, if the jet stream shifts, then the weather will change. Policy and consequence. If the taxes are raised, then there will be a recession, and so forth. But in logic, we abstract from all that to focus on the core logical meaning, which is then used to calculate truth values, with the ultimate goal, in our case, of evaluating arguments for validity. Right? So remember, symbolic language is a formal language, an artificial language. When we use it, we abstract away from all the other features of natural language sentences. But let's try to think our way into this logical meaning of if-then. I mean, the first thing you got to do is just memorize the truth table. But once you memorize the truth table, it's helpful to think about it, to try to develop some intuition or insights into why we're doing it this way. Suppose I make you a promise. If I receive my stimulus check, then I will buy you a Luke Skywalker action figure. And you can tell me whether you want it to be Luke on Hoth, Luke in Return of the Jedi, Luke in A New Hope. But I won't get you an action figure from Luke in The Last Jedi, because for me, that movie doesn't exist. But in any case, we put that into, we first translate it. R, I receive my stimulus check. B, I buy you a Luke Skywalker action figure, but not one from The Last Jedi. And it has the form if R, then B, R arrow B, which has the universal form of if P, then Q, P arrow Q. Now let's consider why I might break my promise, relating that to our truth table. Suppose in case 1, I receive my stimulus check and I buy you the action figure. Well, if P, then Q is true, since I did not break the promise. True, then true is true. Now suppose I receive my stimulus check and I do not buy you the action figure. Okay? I don't think I'd do that, but if I did, if P, then Q is false, since I broke my promise. True, then false is false. Now consider a third case. I did not, fine shouldn't be there. Let me go up on the board and erase that. There we go. Okay. I did not receive my stimulus check, but I buy you the action figure anyway, because I'm just such a nice guy. Well, if P, then Q is true, since I did not break the promise to buy you the action figure. False and true is true. Okay? And suppose I do not receive my stimulus check and I do not buy you the action figure because I have to use my extra money for food, right? Well, if P then Q is true, since I did not break my promise to get you the figure if I receive my stimulus check, right? So false then false is true. Now this might be the hardest one to understand, so first you just memorize it. If false then false is true, but think about that. I did not receive my stimulus check, and I do not buy you the action figure. Well, I did not break my promise. It's false since I did not break my promise to get you the figure if I receive my stimulus check. Now, this is a way to develop intuitions into what this means. But first, you just have to memorize this truth table. These are like the multiplication tables for what we're going to be doing. And just like you couldn't do math without knowing what 9 times 9 is, right? You're going to have to know that if true, then false is false, and so on, to do our calculation. Now, you might be wondering, what about the wiring diagrams and the computers? Well, it turns out all you need is and, or not to have a complete language. And we're going to look at 2 more operators which are not essential to our language, but make it easier to manipulate. Because it turns out the if-then, for example, that we're looking at now, can be symbolized using the not and the or, and so on, right? And so the wiring diagram would just be combinations of not and or circuits, right? Which is fascinating. You can go look that up if you want, but this is not an electrical engineering class, so I'm not going to get into more detail with that, right? But all you really need is and or not to make the computer run, the phone to work, and so on, right? So here we have our final truth functional definition, our final operator, the biconditional. Consider, Luke will become a Jedi if and only if he faces Vader. So we let J stand for Luke becomes a Jedi, V for Luke faces Vader, and that gives us J if and only if V. That's how we'd read that. J if and only if V. And this is called a biconditional. A biconditional is true when both of its components have the same truth value, and it's false. Oh, got to go up on the board. And it's false if both of its components have different truth values. And this is actually one that makes a lot of sense to me, right? If something true, if true is equivalent to true, you can also read that as J is equivalent to V, or J if and only if V, right? True is equivalent to true is true. True is equivalent to false. That just seems obviously false. False is equivalent to true. Well, that seems obviously false. And false is equivalent to false. That's true. So while there's different ways to say these things in the English language, we're going to abstract and have them all mean this, right? So Luke will become a Jedi just in the event that he faces Vader. Luke will become a Jedi if and only if he faces Vader. Luke will become a Jedi just in case he faces Vader. J is equivalent to V. Again, I want to encourage you, all this seems very simple, but it'll quickly become very complicated, and you have to proceed by memorizing and getting really clear on the basic points, right? So you need to memorize those truth tables. You need to be able to write them down. You need to be able to just reel them off, right? True or true is true, true or false is true, false or true is true, false or false is false. If true, then false is false. If true, then true is true, so on. You just need to be able to know those things, right? And to have them at the tip of your fingers, the tip of the fingers of your mind. Okay. So, I'll stop here so you can think about all this, and I'll get ready to record another video for you. Hang in there, and thank you for your kind attention.